Previously, we had obtained the expression for Jacobian matrix. It was an analytical expression. Now we substitute specific values for theta 1, theta 2, theta 3, and theta 4 and obtained a numerical value for the Jacobian matrix. For theta 1, theta 2, theta 3, theta 4, we choose these values 0, pi by 2, minus pi by 2, and 0. And this particular set of joint angles or joint variables correspond to the configuration of the robot that is shown in this figure. You may see that the slider values are all 0, 90, minus 90, and 0 degrees. In the speciality of this configuration is that all the joint axes, this is one first axis, this is the second one, this is the third, and this is the fourth, they all align in a single plane. Coming back to the matrix, how can we relate this matrix to the actual robot? What do these numbers mean? Well, let us see how we can understand this. We know very well when theta 1 dot is 1 and theta 2 dot and theta 3 dot and theta 4 dot are 0, then the linear velocity of O4 is going to be this 0, 3, 0. What this says is O4 would move along a y direction. It will not have any component along x or z direction. And another way of putting the same thing or saying the same thing is, suppose we keep theta 2, theta 3, and theta 4 constant and make a very small change in theta 1, then the velocity of O4 or the motion of the O4 would be along this direction. Further, the rotation of the last frame would be about this axis. In this particular case, this is Z axis. This is what this set of numbers would say. This is based on the meaning from which we derive the Jacobian matrix. Now let us see how far this is true by looking at the interactive app. Now here we have these four numbers. We will not touch these, we will keep them as it is, and we will just vary theta 1 a little bit around its current value and see what happens. Before we do that, we should recollect that O4, which is the origin of the frame 4, is located here. So now here we are changing the value of theta 1. So as theta 1 is being changed, the O4 is executing motion. It seems that the motion is along y direction. Perhaps it can be better seen in this particular orientation. So as we change theta 1, O4, which is located here, is just moving along a straight line. It is just moving along y-axis. It has no component along the z direction, or even, it has no component along x direction, or for that matter, even along the z direction. And if we take a relook at the Jacobian matrix, indeed the first three rows, which correspond to velocity of O4, has only non-zero y component, the x component is 0 and the z component is 0. Indeed, the meaning, we see the consistency in the meaning. The last three columns of the last three rows of the first column says that when theta 1 is changed, keeping the other joint variables constant, the angular velocity is along z direction. This again we can understand by looking at the interactive app. We will if we, by keeping theta 2, theta 3, theta 4 untouched, if we make small changes in theta 1, all the links, that is this red colored, green colored, yellow colored and pink colored, they all rotate about the first joint axis by the same angle. Therefore, all of them have the same angular velocity, but our interest is only on the last one. Of course, that angular velocity is along the z direction, and that is what we see in the Jacobian. Only the z component is non-zero, rest of them are 0. Let us continue our analysis and see what happens when only theta 2 is varied by keeping theta 1, theta 3 and theta 4 as constant. Let us start again from the interactive app. So we will first bring theta 1 value to its reference value, which is actually 0. Here it is 0. Now we change just theta 2 and see what happens to 4. So here we are changing just theta 2, and it seems that O4 is again moving only along the y direction. So we expect the first three rows of the second column of the Jacobian matrix to only have y component as a non-zero element, rest of them will be 0, which is indeed correct here. So this is the second column, these are the first three rows, and here only y component is non-zero, whereas x and z component are 0. Now at this point of time, one might be interested to know why there is this variation of 3 and 2 here. In the first case it was 3, in the second case it was 2. Why is it so? To understand this, let us go back to the app, and let me take the top view of it. So this is roughly the top view. So when we change theta 2, this O4, whatever is there, is rotating about this point. So for the same change in angle, the distance traversed by this is proportional to this length. But in the previous case, when theta 1 is changed, the rotation is happening about this point. So for the same angle, the length traversed by this is proportional to this length. Obviously, this length is larger than this length. Therefore, in the first case, the distance traversed was more, and in the second case, the distance traversed was less. In fact, this length is to this length is in the ratio of 3:2, and that's why we see the difference in the two numbers. Let us continue with our argument. I'll bring back theta 1 to 0, and I'll make small changes in theta 2, and I'll also change the view. Okay, so now I'm changing theta 2. So as I change theta 2, we see that this green colored link, yellow and pink colored link undergo same rotation, of course, about the